Can you hear me okay online?
Yes.
Great, thank you. It's a packed crowd today. Feels like the biggest gig I've ever done. Yeah. That's what I'm going to do. I'm just going to go to remote for a little bit, then come back. Like those old boy bands with the comeback albums. Okay, I'll leave it for a couple more minutes just to get a few people on. I think a few people are still in bed. Okay, so you should be able to see my screen online now. Can you see it?
Yes, we can.
Okay, good. Just takes just a bit rusty after a week off. Okay, so let's get started. So we've kind of done all the fundamental stuff now. Now we move on to maybe the more fun stuff, right? Learning a little bit about how we can employ what we've already just found out in the first half of this course to developing some biological or biologically active polymers. So the first class of polymers that we're going to look at are stimuli responsive polymers. In particular, we're going to look at shape memory polymers. So this really relies on some of your past knowledge of knowing TGs and TMs. They become really important in this part. And most of it is to do with polyurethane. So if anyone is familiar with Dr. Maitland's work, you'll be aware that he has a embolism device which works on the operation of, they are shape memory polymers which expand and contract. And they're built from polyurethane. So we'll see a little bit of that as we go out for this. So shape memory polymers are polymeric smart materials that have the ability to return from a deformed state, a temporary state, to their original permanent state, and it's induced by an external stimulus such as a temperature change. Now, there are a few different types of stimuli responsive polymers. There's thermoresponsive, which is fairly straightforward, right? It reacts to a change in temperature. There's pH responsive, which reacts to a change in pH. So that's particularly interesting when you're thinking about drug delivery mechanisms in different biological matrices. So the pH can differ, so you can get them to trigger. Expand and contract is normally the way that we call triggering to release drugs at a particular site. And then we also have glucose responsive polymers. So they're not really glucose responsive as such, but they are. The example that we'll show you a little bit later on is a kind of hydrogel that is embedded under the skin, which allows you to monitor different glucose levels in the blood. So you're looking at measuring hyperglycemia, so increased levels, and hypoglycemia, which is decreased levels in the blood. There are also, as we'll come across as we go along, there are also some different types of ways that we can modulate the temperature switching. So a common way for the temperature switching is to use something we call an LCST, which is a lower critical solution temperature. There's a bit of a lag for me when I'm writing this, so I'm sorry if it doesn't come out as neat. And that's where, I'm not going to get into too detail, but that's where at low temperature we have these kind of expanded chains. And then at high temperature, we have our, I don't know why I've drawn them as 8s, but they're coiled chains. So there's ways that we can modulate that, and as you see later on, there is different pendant side groups that we can add onto these polymers, such as polynipam, which you may or may not have come into contact with or heard about, which is particularly important in modulating pH and also thermal response. So let's talk a little bit more in detail about the thermal responsive polymers. So they're polymers that undergo a relatively large and abrupt physical or chemical change in response to small external changes in the environmental conditions. I'm not sure exactly where that definition has come from, but it's pretty concise in what it means. Now, if you read around the literature, there's lots of different ways that people will express, or different names that are used for stimuli responsive polymers. So they'll use stimuli sensitive, intelligent, smart, environmentally sensitive. This is an interesting tactic that a lot of researchers use really to guide it towards its target audience when you're trying to publish these things, because you understand there's quite a bit of interchange between what language they use depending on what audience they're trying to reach out for. So I think the most common one that I certainly see a lot is these smart polymers. They use that quite a lot. So we've got different types, and we've been through the different types. So we've got shape memory polymers that we'll go through today, thermal responsive polymers, which is kind of the intertwined in some way, and then pH responsive polymers and glucose responsive polymers as we'll go along. So the first two are the two that we're going to be dealing with today, shape memory and thermal responsive. Oh, there's also a publication under there that gives you a guide to different stimuli responsive polymers and the bioconjugates that they use. So there's we have two different polymer classes when it comes to stimuli responsive polymers. You have the neat polymers, so they're just kind of ordinary polymers. So we have elastomers, thermosets, and thermoplastics. You're all very well attuned now to what they mean. You should even be at the height of your tune moment as you're starting to go through some of the revision and the guide. So you have an idea of what each one of those things do. Obviously now you know elastomers exhibit that viscoelastic property. Thermosets are ones where you've got these chemical crosslinks in there. Thermoplastics, we can heat up, remold several times. So these can be physically or elastically, chemically cross-linked, which is important. And we can fit shape memory polymers into that class. Now, one huge class of polymers that we deal with quite a lot, or well, I don't deal with, but they deal with a lot in the research in the department, is hydrogels. Hydrogels are these physically or chemically cross-linked polymers which have elasticity, which is lost with water loss. So the main thing with a hydrogel is it can retain water. So they can be adapted for thermal responsive polymers, pH responsive polymers, and the glucose responsive polymers. So you can see how this kind of is going to separate out as we go along. So what we're doing is really just introducing you into the different polymer types that we can come across, and then a little bit later on, we'll start to give a little bit of an idea of the different types of applications that they can be used in. So for a stimuli responsive polymers, the shape memory polymers in particular, these are kind of dual shape materials. So they'll have shape B go into shape A. Actually, you can actually get I don't know the best way to describe this, but you can get kind of 3 transitions if you want. But that's normally the maximum number of transitions, so you can have 3 different shapes in there. But the idea is that you have this permanent shape, you program it into a temporary shape, which is shape B, and then you'll apply some heat, and then it will go back to its permanent shape A again. So the programming is a mechanical deformation, so that's adding some kind of stress to the polymer itself, and then you get a fixation of that deformation at a certain temperature. In order to recover it, the external stimulus causes the polymer, in the recovery, the external stimulus causes the polymer to switch from temporary to a permanent shape. Heat is the most usual way to do this, so you can kind of thermally induce a shape memory effect. There's also ways of doing light, electricity, magnetic field, and also immersion in water. I would say actually light, electric, and magnetic also induce heat as well. It's just a different method of inducing heat into the polymers. So you'll actually find that the way that you change the polymer is mostly by inducing a heat change in those things. Light, electric, and magnetic are just kind of 3 other modes of inducing heat in there. So let's talk a little bit about our shape memory polymers. So what we do is we start off with a primary shape for our polymer, and that would be from what you saw before, the shape A. And then we heat it above the transition temperature. Now, this is really important because I think some of the issues that have come up in the past is that people assume that the transition temperature is either a TG or a TM and never both. It can be either. It can be a TG or TM. So this is a temperature that it's responsible for the softening of the switching segments that we'll come to a bit later on for the temporary shape. If the transition temperature is above, we can reshape it because we've got a little bit more flow in our switching segments. And then what we can do is once we've deformed it into a secondary shape, so you can see here it's just twisted. We can call it back down and we can get it to retain that secondary shape. So that would be shape B. Now what we have at the top one is we have this transition temperature that we must exceed in order to establish physical parameters responsible for the permanent shape. So when we're trying to get the secondary shape to go back to the transition temperature, we have to heat it up above the T-perm for those things, okay? So what we're trying to do is heat it above the original transition temperature to get it to go back to its original shape. So we can switch it from A to B to A pretty easily in there, okay? So there are a few different uses for these polymers. So as I told you before, Dr. Maitland has got this neurovascular embolism device, which is based around shaped polymers, and we'll get to that a little bit later on how he makes those things and how he plays around with the different concentrations of isocyanates to the alcohols in order to produce those. We have shape fitting bone grafts, which is Dr. Grunland. And we also have some interesting self-closing sutures by a guy called Robert Langer, who you may have heard of. He's pretty big in the field of biomaterials. So you can see with these sutures at 20 degrees C, they are in a rather expansive form. When they heat them up, they contract, and by contracting them, they close up the wound. So it's pretty interesting there, different uses for it. So what they've also done is been able to commercialize some of these shape memory polymer into medical devices. And one area that it's found quite a lot of interest is in orthopedics. So this is PEEK. It's actually a PEEK molecule. That's why it's called PEEK Altera material. And it's used for the morphic suture anchor. And it's the first FDA cleared shape memory device. So that was in December of 2009. The suture anchor is used to fix tendons, ligaments, rotator cuff, foot and ankle, hand. So it has lots of different uses. But the anchor is inserted through a small incision in its deformed and collapsed state. And then it forms its expanded state once it's implanted. So it's basically triggered by body temperature to expand in that position. So that's a really cool way of showing that the the shape memory polymers have a particular use, and they are being commercialized and accepted by the FDA. Now, as you imagine, there's lots of ways that we can measure these. Unfortunately, I can't get all of this on the screen at once, so I'm going to have to just go up and down a little bit. But we go back to our stress strain curves that you saw before. And what we can do is we can apply multiple different cycles of stress strain to it. And what we can measure from it is we can take three different types of measurement. The first is strain fixity, RF. And that describes the ability of the switching segments to fix the mechanical deformation. So let me just write that in. Okay, and then we have strain recovery. So what we can do is consecutive cycles of this applying the stress on there. And that describes the ability of the material to memorize its permanent shape. And then what we can do is also measure the total strain recovery in the different cycles. So we can run the cycles and then see how it compares to its first cycle. So N is the cycle number for this. EM is a maximum. Oh, this is really. And let me just start another page because I can't get everything under there. let me write that again. So EP plus EPN. And then the only other thing left is EU, epsilon U. Oh, I can't spell cycles. So essentially what we're measuring is when we apply a strain, I'll just wait a second till you've got that bit down. Okay.
Does that say application at the very end, last row?
Yes. Yeah. Sorry, I don't know what it is. I don't know if you can tell, but there is a lag when I'm writing. So I'm 2 words in front of where we need to be. So I only notice a mistake after I've written it. So that is application. Okay. Let's just go to this stress strain curve. So what we're trying to show you here is that we want to get our shape from its permanent shape into its temporary shape, and then we're trying to measure its ability to go back to its permanent shape again. So when we're applying the load in order to get it into its temporary shape, we're obviously heating it above the transition temperature there. And then so that occurs during phase 1. So this is here. And then what we're doing is we're cooling it to fix it in place. So by cooling it, we're then telling it to keep its temporary shape. So we go below the temperature, below the transition. And then what we do is we unload the strain that we've put on it. And that's where our kind of first measurement comes in. So what we're trying to find is what is the ability for that material to retain its temporary shape in there. So at phase 3, we're unloading it, and then you can see that EM on there, or epsilon M, would be where the strain percentage holds when it is holding its deformation. But actually what you're probably going to get is something similar to EU, where it's going to slightly contract a little bit after you start to remove that stress on the polymer. Then once it's in that temporary shape, so it's still in that temporary shape, we then move from 4 back to the start of 1 again by heating it. So what we're trying to do is then recover the polymer from its temporary shape and get it to go back to its permanent shape. So again, we heat it up above its temperature of transition to measure how much it recovers. Now, if it recovers totally, it will go back to the same size as it was before in its original permanent shape. If it doesn't recover, then that's where we can get our value ER from. So we're basically measuring how long it was in its temporary shape to how long it is once we've tried to heat recover it. But what we can do is we can go through multiple cycles. So we're basically trying to measure the shape memory behavior of the polymer. So if we do 1 cycle, and where can we fix it to? Can we recover it? If we do a second cycle again and try and fix it, where can we get it back to? Where can we recover it to? So you can keep doing this continually and continually to work out whether you're getting the original shape back, whether you're getting incomplete recovery, whether you're getting incomplete fixity in there, and whether you can modulate that temporary shape. So it's fairly straightforward. You're just trying to heat, fix, and then recover, heat, fix, recover, and you're trying to measure the effectiveness of your material to do that. So let's go to the, oh.
Could you explain the unloading part one more time?
The unload, so this bit from 2 to, yeah, okay, for 3. So what you're doing is, right, when you're trying to get it into its temporary shape, you're applying, you're going up the load, right? So you're applying a temperature higher than the transition temperature, and then you're cooling it. And by cooling it, you should fix it in its temporary shape. Now, when you unload the force, right, because we've got to apply a force to get it into its temporary shape to begin with. Once we've cooled it and we unload that force, we're then trying to measure whether it retains that shape or not, and whether there is some kind of contraction. So the strain percentage is really, if you think about it, also similar to just making a, you know, if we was using a dog bone, it's like a length measurement, right? Are we managing to keep the same length, or is it contracting slightly once we've removed that force? Does that make sense?
It does, thank you.
Okay, no problem. Let me get rid of this. So you'll see lots of these, you'll see lots of examples for these as we go along. And I apologize now, actually, when we get a little bit further on, there is a little bit of, it's basically just me reading from the slides and telling you exactly what's there, because it's giving you all the information to the different kinds of polyurethane soft segments and hard segments that you can incorporate in order for them to become shape memory polymers. So for each cycle, we can measure the strain fixity and the retention. So that quantifies the fixability of the temporary shape. Are we managing to fix it and retain it in that temporary shape? So it quantifies the ability of the material to maintain and fix a mechanical deformation. After cooling, so the epsilon m after cooling to result in a temporary deformation EU. So what we're trying to say is that does it change shape after we've removed that stress on it? Now, the strain recovery quantifies the extent the permanent shape is recovered at a temperature above the transition. So that quantifies the ability of the material to return to its permanent shape after heating, after the application of a mechanical deformation from one cycle to the next. So what we're doing is we're measuring this over multiple different cycles. Can we apply that stress to it and fix it, and can we get it back to its permanent shape? Now, ideally, if a material exhibits, you know, excellent strain fixity and excellent strain recovery, the RF and the RR should be 100%, which basically is saying that you're getting 100% recovery and it's recovered to its permanent shape. It's recovered to the permanent shape every time, and you're getting really good fixability 100% of the time. Whether that is true of most polymers, I'm sure it's not, but that's kind of the ideal status that you want to get in there. So here's one that I'm going to give you so you can spend a couple of minutes thinking about this. But from the first to second cycle, we see a more significant decrease in the RR, the strain recovery, with increasing number of cycles. Can you explain why there is a decrease from cycle, big decrease from cycle 1 to 2, then after 2 it starts to just plateau out? So have a think about that for a couple of minutes, go through the notes before, and then I'll answer that question for you. So we've got two values on there. The first one that we've got is this RF value. The RF is the strain fixity, so it's the fixability of the temporary shape. And then we've also got the RR value, which is a strain recovery, and that quantifies the extent to which the permanent shape is recovered. So what you can see is from this that actually the fixability is pretty, well, it's really good, right? It's 100%, so we can fix it 100% of the time in the temporary shape that we want it in. But what we see is that as we go through different cycles, the ability to recover the permanent shape from cycle 1 to 2 decreases quite drastically. Why do you think that is? So can anyone offer an answer for that? Yeah. So actually, you would be right, but we don't force it that far. But you're right. If you passively deform it, is it going to go back into the shape? So the answer was, yeah, maybe it's plastically deformed. If we did plastic deform it, then yeah, it definitely wouldn't go back to the original shape. So it's a good answer, but that's not what we're looking for here, right? We're looking for some kind of modulation in that. So what could happen during the first cycle? If we think we've just made the polymer, we've got it into the shape that we want, or a permanent shape that we want, as we start to stretch those things out, what can you imagine is happening internally?
Does this kind of have to do with like the tensile strain curve, or no?
Go on, go into a little bit more detail.
Like how, like the stages of deformation, but I know you already said it's not plastic deformation. So
You are so close. You are like, you're within touching distance. I'll say you're on a silver medal at the minute. I think you're really close to a gold if you can just reach over that line.
like are the chains like aligning in a certain way after that first cycle that prevents it from going back?
Right, I'd probably give you the points for that. Right, so during the first cycle, you're going to experience the most significant molecular reorganization of your polymer chains. So as you saw before, when you stretch those chains out, and sorry, I don't know your name, but you're going to experience the largest change in chain orientation in the direction of the applied stress. So that is exactly what I think you said in there. So that's significant, and that happens during the first cycle. So when we release that stress and we don't heat anymore, the recovery to the original chain orientation is really different. So for subsequent cycles, the net change in chain orientation is not as dramatic because we've done it all in kind of the first cycle. So that was a great answer. Thank you. Appreciate that. Let me write that down on a lag. This is a new iPad as well. I can't believe, why is it so slow? That's a first world problem. I shouldn't. So that's exactly what we said. So then upon right, so just to recap, so during the first cycle, we see the most significant molecular reorganization of polymer chains. So that's the largest change in chain orientation in the direction of the applied stress. Upon release of stress and heat and recovery of original chain orientation is too different. For subsequent cycles, net change in chain orientation is not as dramatic. Cycles, change. It's hard to say all those things in one sentence. Okay, so next lecture, well, not next lecture because you've got an exam, but the lecture after that, we'll move on to talking about some of these soft and hard regions within some polyurethanes and talk a little bit about net points. And then we'll put some of your abilities into practice with interpreting some of the DSCs for these things, which you're now experts in. So that's where we'll be at the next set of lectures. So I'm going to hang around. Someone's got the microphone on. Good. So then we're going to, I'm going to hang around for the next 20 minutes or so. So if you have any questions on the exam, then let me know. If you don't, then you are free to leave. It's up to you. But thank you. So yeah, if I'm going to be around, so you can ask any questions, and then anyone in the room can answer the question if they know the answer.
So I had a question about this actually. So if we're, significantly reorganizing the molecular structure, how are we able to get like almost 100% strain recovery after the first cycle?
After the first,
right at cycle 1.
So I think this one would be representative of, yeah, I think this is represent. I think the x-axis is wrong. So this is exam. I can't write on it, but I think that where that y is that first cycle. So I don't think the dots on cycle number 1 are true.
Okay, so would that be before?
Yeah, because it doesn't make sense, right? It does, what you said is true, right? It wouldn't make sense that it has to occur during the first cycle. So unless it's just going from, cycle 1 starts at 1, then that's fine. But actually then that wouldn't have a strain recovery because it's in a permanent position anyway. So I think that first dot probably should just be on 100%, and that would make sense, right? But we're not measuring a recovery on that first dot.
Okay.
So it has to occur. It has to occur during the first cycle. The first cycle is. The first cycle must be where it occurs between 1 and 2. So that must be the first change that we go through to make our measurements. I think that's right. I'll check that out, but I think that's correct. I'll check it out for you.
All right, thank you.
There we go.
I have a question.
Yes.
So in regards to the solubility parameter, we have like a formula, delta 1 minus delta 2, to know if a solvent, like if it's a good solvent for a polymer to dissolvent, or yeah. So it's delta 1 minus delta 2 has to be less than or equal to 4. Does it matter? Like, is it just the difference, or does it matter? Like, for example, I mean, depending on how the numbers are organized, it can be like -2, for example, if D2 is larger than delta 1. So does that matter, or does it just have to be the difference between them has to be less than 4?
Have you got an example where it is negative?
I guess it just depends on like what polymers, like if a polymer has just like if the solubility parameter of the polymer is greater than the solubility of the solvent. So like, would that matter?
So, I mean, the main thing is that it has to be, so when you did the homework, there was 2 columns there. One was ones that didn't have hydrogen bonding. The second one was one that did have moderate hydrogen bonding, I believe. What you've got to do is match it up first on those things. And you just want, the idea is, and the best way to do it is just to get the number as close as possible to your polymer number. So, you know, if it goes negative on those things, I'm sure there is a chance that it will still dissolve. But you've just got to get it as close to your polymer as possible, certainly within 4.
Okay, thank you.
I don't think there is any examples. Maybe there is, and I've missed them, but I don't think there is many examples where I haven't given you the options to be +1 or +2.
Got it. Thank you.
Okay. Just to clarify, I probably won't give you any examples where you have to go into negative numbers to make that decision. Any more questions?
I have a question.
Yeah, cool.
So in module 5, the one about TM and TG, one of the slides says lack of bulky or rigid groups in the backbone for TM, but I thought when we had those, like the rigidity in the backbone, that was something we like that would make it more crystalline.
Depends on what it is. So give me an example. What is that? What is a pendant group that you've got in there?
Well, it says bulky or rigid groups. So
Okay. What is a bulky rigid group?
I don't know. I was just thinking of like a ring structure.
Okay, yeah, just like phenol group, right? So if it's got those bulky groups, then yeah, that can increase the melting temperature of those things. If it's something like a long chain, which is kind of carbons extended out, then your chains won't get close enough together to form crystalline regions, or they won't form many of them.
So
That's
I
bulky,
just
that's bulky and flexible.
right. So I guess maybe I'm just confused about the wording. I just don't understand why it says lack of.
Maybe I'm okay. Let's have a look. What slide is it?
I don't know what number it is, but it's kind of towards the end.
This one?
I think I remember this one. I asked the same question when it happened, and you just said it was a list and it wasn't saying that this leads to more crystal.
Oh, right. Okay. Yeah, so that is, yeah, we discussed that. Yeah, the wording needs to change on that.
I think you just passed it.
Oh, I just passed it.
Mhm.
Tell me when to stop, because otherwise.
I think it's on slide 32.
32. Crystallinity, little or no branching. Yeah, this is just a list. This isn't like it isn't like if there is or if there isn't. This is just a list of things that change the crystallinity in the TM.
Okay. Thank you.
Okay, but yeah, you're right. The wording of that needs to change. So I've already written that down.
I also had a question on this slide.
Right.
So we see that HGPE, a lower molecular weight, leads to a higher crystallinity, which I believe also leads to a higher TM. But doesn't a higher molecular weight lead to more intermolecular chain interactions and lead to a higher TM?
So again, this one is just the list. So I would avoid this slide. Don't read this slide. That's probably the best advice I can give you. But you're right. So when we go to low density polyethylene, and we have lots of these short branches, it doesn't pack as well. And the high density has less branching, so we can pack it so it's more crystalline. That's why it's at 70 to 90%. The ultra high molecular weight actually does have a smaller bit of branching in there, but it's a high molecular weight. Yeah, don't read too much into that one. All right. So the best information from the polyethylene is actually from the work that we did in previous slides. So yeah, don't read too much into this one. I think the wording of this needs to change, and that's something that is on my list for next time we teach it.
So how does molecular weight affect crystallinity?
Will you explain to me how do you think it affects it again?
Higher molecular weight is higher crystallinity?
And that is neglecting, and what are you talking about? What polymer?
Oh, does it matter? I guess, does it matter on the polymer?
Probably, yeah.
Oh, it's not just a general trend?
No, no. So it depends on the polymer that you've got in there, right? I'm so annoyed this slide is still in there now. Don't look at this slide. Get rid of it. The wording needs to change on these things, so don't let it confuse you. But you're right for maybe something like high density polyethylene, right? You can, if you are you haven't got branching, you've got a higher molecular weight, there is going to be lots of more crystalline regions in that.
I had a question for lecture 5, slide 21. It talks about where it's like the mono substituted versus di substituted.
Yeah.
And the di substituted is higher crystallinity but lower TM.
Yeah, this question was asked in the last lecture. So let me just go over that. So actually, so you're going to ask me why those are occurring in that way, right?
Mm-hmm.
Yeah, I'm not entirely sure. So that's something that I need to check out. So I think it's something to do with the electronegativities and the balance of those electronegativities. But this, I think it's the case that I need to go to one of the actual publications that's calculated these values to work it out. But just take it from this that it is, and then I'll try and get clarification for the future as to why.
Okay. And this is only for like the mono and di substituted?
Yes.
Okay, sounds good.
Any more? Good. No more? Okay. Good. And I will catch you on Friday. I was going to send an announcement out with the rules for the exam, so we don't take up too much time when it comes to doing it.
I just had a quick question, not about lecture, but about the videos.
Yeah, go on. Sorry.
Are you gonna post the videos from this past Monday and Friday?
Probably not. Do you need them?
My Wi-Fi was just going out all day Monday, so I didn't really get to pay attention to lecture very well, so I was just wondering.
Yeah, okay. Well, I'll put them on there. That's not a problem.
Okay, thank you.
Okay, cool. Done.
I have a question about the test. Are you like posting the link for taking the test on the Canvas?
Am I post? Sorry, sorry, I didn't hear you there.
You're providing us like a link so we can go like take a test on Friday.
No, you'll take the test during the class, and I will post the link when the class starts.
Also,
So
we have to like join the
that'll
Zoom.
Sorry.
So we have to join the Zoom to find out the link.
Yeah. So you all need to be on Zoom. So we're not going to lock down your computers, but you all need to be on Zoom to take the test, and you all need to have your cameras on. So what I'll do is during the announcement, I'll let you know what criteria there are for taking the test.
Okay, thank you.
Okay, but you'll have all that information beforehand, so we don't have to discuss it in class.
Thanks.
Cool. Not longer than 50 minutes worth. Yeah, it's hard. Someone else asked me that question a while ago, but we're going to try and keep it so you should be able to answer 50 minutes worth of questions. But yeah, it'll be less. Why? What you worried about? You worried there's going to be too many, or? I just like to prepare yourself for a set number. Well, I think it will be, I would say, about 7 questions or so. But then some of those questions might have a few parts to them, right? So I don't know if that helps you out or not. But it's 50 minutes if if you've gone through your detail, if you've gone through all the lectures and stuff, there is nothing in there that should surprise you. Obviously there is some to challenge you a bit, but there's nothing that should be in there to surprise you.
One, like, I guess last quick question. In lecture 4, there's like the molecular weight, like equations and stuff, like pi over c equals RT over mn. Do we have to memorize this?
Well,
or
you
just
can
like
if you
know?
want, but no, there's no point in memorizing all of those.
Okay.
I'm not going to ask you any of those things.
But like just know how like the graphs like work, I guess, with the slopes.
Yeah, exactly. Yeah, you got to know how the graphs are constructed. That's the most important thing. The most important thing to me is that you could make a readout from a graph and infer some information on it. That's the most important thing.
Good. Thank you.
Okay.